Hello. Hello and welcome everyone. Thank you for joining us today. I am Iñaki Herrero, Managing Director for Enertis Applus in the US, and I'm excited to present our webinar on energy storage systems at peaker plants. Before we start, just a couple of housekeeping items. We will go for about 45 minutes and we will have time for questions at the end. There is a chat where you can type questions at any time. And we're also going to record the session and it will be shared on YouTube and on demand if you're interested. Let me start by introducing our team of presenters. As I said, I'm Iñaki Herrero. I'm the Managing Director for Enertis Applus in North America. I bring about 20 years of experience with a heavy focus in renewable energy. I have worked with several different technologies such as PV, BESS, wind, CSP, hydro, and biogas. Our main speaker today is Will Lowers, Head of Energy Storage Technology here at Enertis Applus. Will is a leading voice on energy storage in the US. He brings a tremendous amount of experience in this subject, and over the past 10 years, he has worked on hundreds of storage projects across the US and Canada. Will has also worked on energy policy, playing key roles at the Massachusetts Department of Energy Resources. We also welcome Umed Paliwal, scientist at UC Berkeley. Umed's research focuses on renewable energy integration, electricity markets and policies, as well as electric vehicles. He has played a key role in several high-impact energy modeling studies that have shown pathways to rapidly decarbonize the US electricity sector and transportation system. Umed is also a recipient of the Berkeley Labs Director Award for Exceptional Scientific Achievement in Societal Impact. Last but not least, we have Priscilla Bell, our data science specialist here at Enertis Applus. Priscilla leads our efforts in modeling PV plus storage systems and brings over 10 gigawatts of experience working with these technologies. Today, we are talking about co-locating energy storage systems with existing peaker plants. These plants offer a significant advantage for the development of new storage systems, as they allow for accelerating interconnection review, reduce permitting risks, and lower capital costs. All of these make these sites ideal for energy storage deployment. We will start with a very brief intro to our company, and then we will dive into the core of the webinar. And as I said, we'll have time for questions at the end. Just a bit about Enertis Applus. We are a full-service consulting and engineering firm for renewable energy projects. Our services include independent and honest engineering, vendor inspection, conceptual designs, testing, and data analytics. We are part of the Applus Group, which is one of the world's leading testing, inspection, and certification companies, with over 25,000 employees in 70 countries. Our company brings 20 years of experience and a global track record of over 850 gigawatts and 100 gigawatt hours of storage. And with that out of the way, I'm going to hand it over to you, Will.
Thanks, Iñaki, and welcome everyone. I'm going to provide a quick background on the context of the opportunity, and then we'll dive into some of the details. So for background, the electric grid is a just-in-time system, meaning that electricity is generated when it's needed. So as a result, the entire system needs to be sized according to the multi-year ahead conservative peak forecasts. And that sizing includes transmission lines, power plants, and the associated interconnection infrastructure. All generators and power plants are required to have an interconnection agreement, which is the contractual right to inject electricity into that point on the electric grid. And it also represents the physical infrastructure required to enable that injection. So the electric grid today is able to serve peak electric demands of today, meaning there are sufficient electric interconnection agreements serving the infrastructure that we have of today. Next slide, please. So while all of those interconnections and all of that infrastructure exists, traditionally, whenever a new power plant wants to come online, such as wind, solar, or a battery, they will file for a new interconnection agreement with new interconnection infrastructure. So they do that by submitting a request to the host utility, and they get in line, which is known as the queue. And so over the past decade or so, the queues have really become backed up. There are now over 2,000 gigawatts in queue across the United States, with an average time in queue of several years at this point. And there's currently less than 20% success rate from projects entering the queue early development to those that actually get built. And the costs associated with those approved projects have been increasingly rising. So it sounds like a pretty unpleasant experience. Meanwhile, existing peaker power plants are generally substantially more expensive to run, and they are inefficient when they operate. And so as a result, they are dispatched pretty infrequently, and some can have an annual utilization rate rounding down to as low as 0% in a given year. So the firm delivery LGIA that those peaker power plants have and the interconnection infrastructure they're sitting on has substantial value, but it's currently being underutilized. Next slide, please. At the same time, while those queues have been getting clogged, battery energy storage has seen a substantial cost decline over the past several years. Energy storage densities have improved so that more storage can be fit on the same or smaller parcel of land. And many energy storage systems, the designs have been improving incrementally year over year, and they're approaching a more appliance-like containerized approach, supporting a much faster delivery, cold and hot commissioning process. So all of that to say, the opportunity as it presents today is very ripe. Now I'd like to hand it over to Umed of UC Berkeley to discuss his research on the opportunity and how they identify the sites.
Next. Thank you, Will, for that great introduction, and thank you all for being here. So we at UC Berkeley conducted a study to estimate how much new capacity can be added near these underutilized existing power plants. And this study is much broader than just looking at peaker power plants. It includes all thermal and renewable power plants in the US. And the motivation for the study kind of came from after looking at the significant load growth projections in the US and the massive interconnection queue backlog, as Will mentioned. So the peak capacity in the US is expected to grow by around 128 gigawatts by 2030. And there is a lot of interest from developers to meet this capacity, to meet this load growth. As Will mentioned, that there are more than 2,000 gigawatts of projects right now in the interconnection queue. But the problem is that this interconnection queue is significantly backlogged. Today, it takes 3 to 4 years for a new project to get connected to the grid. In addition to the interconnection issues, there are significant supply chain challenges as well, especially for gas power plants. So today it takes around 3 to 4 years to procure a gas turbine. Combine this with supply chain issues in transformers and the interconnection issues. We estimate that any new gas plant ordered today would not come online before 2031, 2032. And the result of all this is there is a real possibility of capacity shortfall in the coming years. And the markets are highlighting that. We have seen that the capacity market prices in PJM have almost 10x in last 2 to 3 years. We have seen similar capacity market price increases in MISO and ISO New England as well. Next slide, please. So what can we do about it? So while there has been a lot of effort in reforming the interconnection queue to get the projects connected faster, we think there is an overlooked opportunity, which is that the interconnection capacity of the existing power plants is significantly underutilized. To give you a statistic, of the 700 gigawatt of thermal capacity in the US, 200 gigawatts operates at a capacity factor less than 15%. Meaning for 85% of the time, that 200 gigawatt of interconnection capacity is essentially idle. The story is similar for renewables as well. US has around 350 gigawatts of renewable capacity installed, but the average aggregate capacity factor of that renewable capacity is around 22%. So meaning for more than 75% of the time, that 350 gigawatts of renewable interconnection capacity is essentially idle as well. Renewables actually underutilize their interconnection capacity from a firm capacity perspective as well. So we looked at the 5 major ISOs, and what we found is that there is around 190 gigawatts of installed renewable capacity, but only 50 to 55 gigawatts is counted as firm capacity because of the intermittency issues. So what if we could add new solar, wind batteries, or any other new resources near these underutilized existing power plants? And that's essentially the idea of surplus interconnection service. So building new resources near the existing power plants such that these new resources share the same interconnection of the existing power plant. This idea of surplus interconnection was introduced by FERC in 2018, and there are already multiple projects underway trying to take advantage of this opportunity. In MISO, there is around 5 to 6 gigawatt of capacity already in the queue trying to take advantage of surplus interconnection. We have seen in California, multiple gas plants have installed battery storage to their existing interconnection. And similarly, right now in PJM, there is a lot of interest from battery storage developers to add batteries to the existing renewable plants to meet that peak capacity growth that is happening in PJM. And this idea of adding battery storage to meet peak capacity is both economical and faster than the alternative of building new gas plants. So we took a look at comparing 6-hour battery storage with building new gas plants. And what we find is that 6-hour battery storage is 30 to 40% cheaper, especially right now with IRA incentives. It takes 1 to 2 years as compared to 6 to 7 years for new gas plants. And they have comparable ELCCs almost across all ISOs in the US. Next slide, please. So in our study, we wanted to see how much new capacity, specifically solar, wind, and battery capacity, can be added near the existing power plants in the US. So to do this, we specifically wanted to answer 3 questions. First, is the land available near the existing power plants to develop these new resources? So to do this, we took more than 50 different high-resolution satellite data sets and estimated the land use near all of the thermal and renewable plants in the US. Second, we wanted to estimate what would be the economics of these new resources at the existing power plants. So we took meteorological data from NASA, European Space Agency, to simulate the economics of these new resources at existing power plants, and then comparing it with what does the economics of existing power plants look like in comparison with these new resources. And finally, we estimated how much new capacity can be added given the operational constraints of the existing power plants. So the ramp rates, their minimum runtime, and so on, but while also keeping the curtailment of the hybrid system less than 5 to 10%. And what we find is that for renewable power plants, if you were to add 6-hour batteries at all the existing renewable power plants in the US, we can add around 260 gigawatts of battery storage capacity. But this also enables addition of around 360 gigawatts of additional renewable capacity at the same renewable interconnections. So we get around 260 gigawatts of new firm capacity that can meet the peak growth, but we also get 360 gigawatts of new electricity that can meet the electricity demand growth as well. Similarly, for thermal plants, we estimate that we could add around, if we were to consider the IRA incentives, around 1,000 gigawatts of RE near the existing thermal plants. And without IRA incentive, these numbers drop to around 600 gigawatt, but still a huge number for the US. Moving on to another opportunity, a lot of the load growth today is coming from the data centers. This concept of surplus interconnection can be used to power data centers faster as well, as time to power is the core of the opportunity here. And the way it works is the data center is located behind the meter of a gas peaker plant. But in addition to the data center, the idea is to locate oversized solar and around 15 to 16 hours of battery as well. And the way it would work is for 90 to 95% of the time, the data center gets power from solar and storage. But for 5 to 10% of the time, when solar and storage are not available, the gas power plant acts as a backup to the data center. In this case, the gas plant has a dual role. It provides power to the data center, but can also supply power to the grid in times of stress. Next slide, please. There is a lot of policy momentum to streamline the surplus interconnection process across different ISOs in the US. So earlier this year, we saw PJM simplified its rules to make it easier for developers to add new capacity at existing power plants, and specifically the addition of batteries at the existing power plants. So now in PJM, developers can add batteries to existing power plants. These batteries can be charged from the grid, and these batteries can be added as soon as the interconnection agreement of the host plant is signed. And the developers don't have to wait for the host plant to have commercial operation. Similarly, in California, a few months ago, a new legislation, AB 1408, was introduced. And this legislation asked California ISO, the PUC, and the utilities to consider surplus interconnection in their further planning processes. Similar policy work is happening in MISO and SPP as well to make this process easier. So there is a lot of regulatory and policy interest from the regulators to make this idea happen. Next slide. And finally, all the results of our study are available at our project website, which is scarcity2surplus.com. On this website, you will find a web dashboard that have details on all the power plants in the US, both thermal and renewable. So you'll find plant level capacity, their historical capacity factors, their LCOE, variable cost, economics. But in addition to that, you will also find what does the land use near these plants look like, how much new capacity can be added, and the economics of this newly added capacity. Thank you, and back to Will.
Thanks, Ahmed. So when we talk about adding energy storage to peakers, there are generally 3 configurations available to the plant. On the far left would be putting the battery behind the existing LJA and existing infrastructure, which is the primary focus of today. This is generally the cheapest and fastest configuration. However, it does come with some operational constraints between the battery and the thermal plant. On the far right is shown there are other opportunities where a thermal peaker may want to add a battery behind new substation infrastructure, a new main power transformer, and a new LJA. The benefits here being you no longer have that operational constraint between the 2 plants. However, you are subject to the internet connection queue and the timelines associated with infrastructure. So not the focus of today. However, there is a role for that. And then in the center, there are some opportunities where a facility may want to both have some storage behind their existing LJA while also adding additional storage to the site if they had additional land and they were aware that the local transmission system had that excess hosting capacity available. So as we've noted previously, an interconnection agreement is a contract, and as a contract, it can be amended if all parties are agreeable to it. So the ISOs generally have standardized the process for those amendments, for example, calling them a material modification assessment. And that MMA is to assess whether a proposed change to a facility rises to the level of being a material modification. This is very common. It's a very common process early in project development when you're changing what inverters you've selected, when you're changing project designs. It's very common to go through multiple MMAs before finally having that final executed LJA that the plant will operate under. That same process is available to existing LJAs for existing power plants. And if the update is deemed non-material, the project can effectively proceed with those proposed updates immediately as if they are approved without going through the interconnection process. So effectively, this is an alternative viable pathway instead of the interconnection queue. If that proposed change of adding energy storage is deemed to be material, then there are some potential pathways where the project would need to file and enter the interconnection queue. So this opportunity may not be equally present to all plants. However, there definitely have been some instances where the MMA process has proved fruitful for projects. Next slide, please. So the primary competition to siting storage at existing peakers would be standalone storage, which are also obviously being deployed at scale rapidly today. And so there are three primary advantages to this opportunity of storage co-locating with an existing thermal plant. And that is, it can be faster, cheaper, and lower risk. So we focused a fair amount on interconnection. And again, as noted earlier, the interconnection process is a several-year process with a substantial amount of risk and a lot of projects that just never make it through to the other end. So very long, very high risk, and also whatever upgrades are identified, the project is going to need to pay for. The California CAISO recently published a study on their interconnection MMA process, and they found an average of 3 to 4 months for MMA processing and MMA approvals. So we're going from 3 to 4 years to 3 to 4 months on timeline for interconnection. And as soon as you have that MMA result in hand, you've de-risked a substantial amount of the development risk, where typically you've got that only 20% of projects making it through the other end of interconnection. You also have an accelerated and lower risk permitting opportunity. A lot of these peaker power plants are subject to sole jurisdiction of energy facilities siting boards, which is typically a state level sole jurisdiction for these plants, where these facilities are already industrial, already commercial use, and already energy facilities. The permitting process can be greatly simplified and potentially lower risk for the project. And then finally, as we've noted, you're leveraging the existing main power transformer and substation and interconnection facilities. So obviously you're gaining speed there and saving money. It's cheaper. And there's also a lower risk profile where the MPT supply chain recently has had both growing costs, but also growing timelines. And so really 3 of the longest lead time items for a standalone storage development are substantially addressed in this opportunity. So these projects could come to market much faster than a standalone equivalent project. Next slide, please. So if it's such a great idea, why aren't we seeing it everywhere today? And to that, I would answer, it's just begun, but it is real today. So earlier this year, the Middle River Power Group announced their acquisition by Partners Group. And part of that announcement was a 1.9 gigawatt generation portfolio that they are converting into hybrid energy centers pairing with energy storage. And they've separately had now several announcements with projects already coming online this year. So there are demonstrations of this successfully occurring today. We've also seen other major announcements this year, such as Ameren's new simple cycle peaker, where they have decided to pair it with energy storage as a hybrid energy center. And several other IPPs have announced their intent to develop very similar projects, both with new plants and with existing thermal plants. And then, as Umed brought up, hyperscalers have been buying power plants as of late. So one example would be XAI's recent purchase of a 640 megawatt gas plant. They are also pairing that with substantial storage to buffer between the on-site demand, local grid conditions, and that power station. But while the use case is slightly different on the storage, the commercial play is effectively the same. It's about speed to power. And the opportunity here, as presented, is a speed to power opportunity and advantage. If a thermal plant owner sees the market opportunity for storage in the near term, they can develop that storage substantially faster and respond to that price signal faster than a standalone development would be able to. So as noted, there are many gigawatts of opportunity here. So I would expect the opportunities and announcements to only accelerate. And I do think it's going to surprise many people how fast these projects come to market and come online, given the schedule advantages that they have through this process. Next slide, please. So while energy storage, while the opportunity is massive, I think a lot of plants will be investigating this and are currently investigating this. Energy storage is complex. It's a complex technology. It is a dispatchable digital asset that also has physical degradation considerations. There are many primary agreements that go into the development of these projects. And so there's a lot to think about from the very first ideation stage of one of these projects all the way through to the actual construction and operation. And so I do want to make it readily apparent there's a lot of complexity and a lot of thought that goes into these projects. And our team at Enertis Applus is here to help ensure project success. So we can support from the early ideation stage through RFPs, through major agreement development, and then all the way through construction. Next slide, please. And while storage has gotten substantially cheaper over the past several years, it's still a pretty large capital expense. So typically we still see a classic renewable style of financing approach, which involves both construction debt and a tax equity lender involvement in the development of energy storage. Energy storage, I'm sure everyone is aware, will continue to have access to the investment tax credit in the coming years. So where other renewables may be leaving from that policy side, there's going to be a tax appetite for energy storage, and storage paired with thermal peakers is equally eligible as a standalone storage system. And so one thing that I would just want to highlight for everyone on the call is both construction debt and tax equity require a due diligence report from an independent engineer. And Enertis Applus is a trusted partner in providing independent engineering services, both for the plant owner and for the lenders involved. And with that, I think we'll be moving into questions and answers.
Yes, thank you so much, both Umed and Will. So everybody attending, please put some questions in the Q&A. You can direct them towards Umed or Will, and I'll facilitate this. So we've got one right now. What are the advantages and unique benefits of adding surplus storage to existing thermal versus adding to existing renewables? Will, do you want to take a stab at that first?
Sure. So I guess one of the advantages of adding storage to an existing thermal is typically thermal power plants are going to have a firm delivery commitment in their interconnection agreement. So they have the right to inject to the grid at nameplate power at any time. So there's an opportunity there for storage where very likely you're going to be, because you already have firm delivery, it is maybe less likely you're going to be found to be a material modification as you apply for making that revision. Though obviously there's opportunities for both, and happy to turn it over to Umed.
Yeah, sure. So for renewables, the advantage is, so right now, if it's a standalone renewables, they don't get a significant capacity value or ELCC across all ISOs. The typical values for storage are around 10 to 15%. For wind and some ISOs, they are a little bit higher in the range of 30 to 35%. Adding battery storage, so battery storage has significantly higher capacity value ELCC. So adding battery storage to the renewables increases the capacity value of that hybrid system. So there is an opportunity for taking in those capacity payments, so it increases the revenue significantly. For thermal plants, as Will mentioned, there is the arbitrage opportunity, especially at the existing peaker power plants, which are very expensive to operate. Like for renewables, like there needs to be like some study on like deliverability to get that capacity rights to the storage in some ISOs. For thermal, this process would rather be easier because the thermal plant already has a significant capacity value.
Okay, thanks, guys. Kind of in line with what you were just talking about, Umed, we received a question. How do ISOs determine the ELCC for a peaker plus BESS plant? Is it the higher of the two, or what's the thinking there?
So, I mean, like this is not significantly clear like right now. The ISOs are still trying to figure this out. Like in some ISOs, they take maximum of the two, like, and there is also some preference from the consumers as well. But this is still an area of development.
Okay, thanks. How are generator models typically required during an interconnection study? How are these affected when BESS is co-located with thermal generation? Yeah, Will.
Sure. There can be a few potential implications there. So the models could show potential harmonics and interplay between the storage and the existing generation. Typically, that's more of a concern for new storage sited close to an existing thermal peaker or in a new interconnection right next door in the same substation. Because of the opportunity I was talking about earlier today, because they're behind the same MPT, they would generally have a relay. So it's either or the thermal plant or the storage operating at any given time. So you're not going to find that harmonic as a result because they won't operate at the same time. You could find some generator model issues come up, which again could get you kicked out of the MMA and into the fuller interconnection process. So it is a bit project specific. I would say the more likely cause for potential rerouting out of MMA is a thermal plant doesn't ever act as substantial load on the system, whereas a battery does act as load when it's charging. And so that is a potentially material change to your LGIA, where those studies could identify that as an issue.
Okay, thank you. Another question directed for you, Will. Are you imagining that the storage system will charge from the grid or charge from the peaker plants when they are not exporting? This is kind of in line with what you were just talking about. Otherwise, this person would expect, again, that the interconnection would be a material modification. So I guess the question generally here is, yeah, that could the battery charge from the peaker plant, or is it limited to the grid?
Generally, it would be limited. There are opportunities to enable them to co-participate, but you're going to have to then use some type of a protective relay scheme to make sure you're respecting that POI limit. So there are opportunities really either way. Generally, you don't want to be charging from the peaker because the peaker is so inefficient and so expensive to run. That's why it has such a low capacity factor. And so you don't want to charge a battery off the least efficient, most expensive energy. You want to charge the battery off the cheapest energy you can get, which is probably earlier in the day off of excess renewables or some other time of day to charge. So actually part of the economic play here is you're probably going to reduce runtime on your thermal plant and more often be cycling the battery because it's cheaper to charge your battery at wholesale rates, pay the lower rates, charge the battery, and then discharge them later in the day. That's cheaper than accounting for wear and tear, O&M, and fuel on that more inefficient peaker. And then I guess one quick point I forgot to bring up on the generator models. there can be a number of complexities there. So another is some peaker plants maybe aren't currently modeled as a continuous generator. Maybe the way that the energy storage is going to operate in the market will be continuous generator. So there can be implications on the existing metering infrastructure and the rig that you have. So while primarily the construction is going to be on the storage, there could be some changes required on the thermal plant to support that model.
Okay, thanks, Will. Next question is, how do you view third-party renewable IPPs interacting with firms who are implementing BESS with peakers?
Do you want me to start?
Yes, please.
Okay. I think the opportunity here is pretty massive. So I would say generally renewables developers and renewable IPPs have a good feel and understanding of the tax equity process and developing responsive to policy incentives, while most peaker development has not had to respond to that and is maybe less familiar with some of the development requirements, some of the safe harbor provisions, independent engineering reports. That entire process maybe is a little bit foreign to them. So there could be opportunities for partnerships here. I think there would be opportunities for both parties to learn. I would not be surprised if we see some mergers and acquisitions. It could be traditional thermal IPPs buying renewables developers. It could be more traditional renewables IPPs buying thermal assets specifically to gain access to those existing interconnection agreements. So there's a lot of opportunity either to be working together or even to be purchasing each other out.
Yeah, interesting. What would be the first steps as a thermal owner if you're interested in taking advantage of this opportunity?
I would say likely first steps would be just an initial evaluation of the feasibility, economic of feasibility. So what market are you in? What price node are you in? Where are prices trending? What's the arbitrage opportunity? What is your current contract status? Do you have an offtake for your RA or for your capacity, or are you selling it in the market? So there's a lot of sort of the early stage investigation to do, evaluating your current capacity factor. Are you trending up, trending down? Where do you see your plant in 5 years? And then how would that change with storage? So I think those would be some of the first steps probably. And then from there, probably starting to figure out what are the market prices for storage, what is the development process, and becoming more familiar with what would the actual development of a project and management of that project look like.
That makes sense. Umed, in your study, was part of the scope understanding the grid charge rights, and would that be easier at some locations versus others? Is that easier at thermal versus existing renewable plants?
So we didn't specifically looked at grid charging, but like in the case of renewables, the idea would be to charge directly from the renewables and not from the grid, because then you can potentially avoid some DC to AC charging losses, and you can also get like much cheaper electricity like from that like existing renewable facility. But I anticipate if grid charging like is the need, like I think it should be difficult in both the cases. But like I think the bigger opportunity, especially for adding battery storage to existing renewable plants, and there needs to be some clarification for rules, at least in California, is that how, like when do these batteries get the capacity value, because that is the major source of revenue. And like at least in California, these batteries are initially treated as energy only. So there is some effort right now to get these batteries capacity value a little bit faster.
Okay, thank you. So we have a question regarding the finances here. So would the project level returns for standalone systems be better than co-located? And do we have a ballpark for that difference, or I guess do we not expect those returns to be different? This can either of you who has a response there.
I'll start and then hand it off. I would say the returns will be different, but the returns for all projects will be different. So, for example, for a standalone project, again, if only 20% of your early stage developments are making it through the interconnection queue, those other 80% of projects, the development cost of those projects is supported by the eventual sale price of the projects that do make it through. So it's not like we're just, have a bankruptcy mill going through the interconnection process. The successful projects have to cover the cost they spent elsewhere on unsuccessful projects. So there is that additional cost that's not represented here. And then also you've got the capital savings on the main power transformer and on the substation. On lost revenue side, if you're behind the existing LJA, then the new storage is not going to be getting capacity credits or RA, because that thermal plant is already getting full RA or full capacity. So the storage asset may be a lot cheaper up front, maybe much faster to bring online. So maybe you're getting online 2 years sooner or 3 years sooner than you would with a standalone asset, but you're going purely on an arbitrage play because your RA is already sold off from the thermal plant. So the financial model can look very different. Hard to say where you're going to get the faster return. I think a lot of that depends on what are those interconnection upgrade costs. How large is the plant? Again, if you're looking to develop a gigawatt or larger standalone storage, then if you wanted to find the thermal plant equivalent, you're limited to only looking for gigawatt plus plants. You're going to find yourself pretty limited, and you're not going to find peakers. You're going to find base load plants. So a lot of this is sort of what is the right size of development for you, and then whether or not speed to market is a value in that region.
Yeah, I think I'll just add that we're not sure about returns, but like the costs can certainly be lower because a lot of transmission infrastructure, substation infrastructure, planning, modeling, land, can be reused. So that brings the cost a little bit down. And this is also seen in the data as well. If you look at the interconnection queue data, most of the renewable capacity, or at least the solar capacity that is coming in the Southwest, is paired with either 2 hours or 4 hours of solar capacity.
Thank you for those insights. Another question about your study, Umed. So your study highlighted a 6-hour battery. So is there an optimal battery storage capacity, 4 hours versus 6 versus 8 versus 10 that was found, or why did you go with 6?
Yeah, so the decision for going for a 6-hour battery was just our own. There could be different optimal sizes, but our idea was 6-hour battery because the need of the day is increasing that peak capacity. And what we have found across different ISOs is that 6-hour batteries get significantly higher ELCC. In PJM, it gets around 60%. In other ISOs, it gets around 70 to 80% ELCC as well. So very comparable to what a combined cycle or a peaker gas plant would get. So that was the idea. Still today, 6-hour batteries right now not so much in development. Maybe in Australia, there is some 6 to 8-hour batteries development happening. But the same results can also be achieved with 4-hour battery as well, because 4-hour battery also gets significantly higher capacity value than standalone renewables. And the greater opportunity that it allows for additional renewable capacity to be added at the same interconnection, because battery can now smooth that renewable output from the day to the night. So more renewables can be added, and that increases the utilization of the interconnection, bypassing the interconnection queue backlog to bring these projects online faster.
Okay, thank you for that clarification. Another question for Umed. What would you say are the biggest opportunities for large data centers in increasingly capacity constrained markets?
So I think like one solution that we have been thinking about is like what I said in the presentation, that locating the biggest issue for data centers is getting power, and like that is the bottleneck right now, as everybody, all the CEOs keep saying all the time. So this idea of locating the data center behind the meter of the power plant, but also pairing it with renewables and oversized storage. So that can fill like bunch of imperatives. It can solar plus storage is like can be deployed much faster. So these data centers can be powered much faster. Solar plus storage, if you can size it, can get to 90% clean electricity. So a lot of these hyperscalers has mandates or goals to get as much clean electricity as possible, so they can get power faster, cleaner, and this can happen like in 1 to 2 years as compared to 5 to 6 years right now. And
Yeah,
one more thing,
definitely. Yeah, keep going.
like in terms of cost, I mean, we estimated the cost of the system, and like it doesn't really break the bank. Like we estimate that the average electricity cost can be in the range of 10 to 12 cents a kilowatt hour, which is very comparable or even lower than the industrial electricity rate in a lot of states in the US.
Yeah, clear advantages, I think, from both of your presentations. Are there environmental benefits of co-locating with a peaker plant? Is there a way to quantify the emissions that are reduced, or the avoided cost?
Sure.
Is that a will? Yeah.
So where there are operational constraints, it's either the battery cycling or the thermal plant. Most of these peaker plants are located in somewhat urban environments, close to load centers. So, and a lot of them are inefficient, meaning they have fairly high emissions rate, including criteria emissions rates when they do operate. There have been a number of policy initiatives specifically targeting peaker power plants because of that, because of the criteria pollutants in environmental justice communities, and looking for alternative ways to meet those peak demands instead of cycling those plants. And generally, while the opportunity here to add a battery to that plant, the idea would be to maintain that plant and have it in an operable state. So you do have that flexibility in the future to operate it as necessary. Generally, the expectation would be a lower and lower utilization of the thermal plant in the coming years, with the energy storage capturing the majority of the arbitrage value available in the market.
Okay, thank you. In general, I guess, would we advise standalone BESS? Let me read this again. Would you advise co-location of standalone BESS or hybrid PV plus BESS assets with, I think, okay. I think it's asking about standalone batteries versus hybrid PV plus BESS or peaker plus BESS. So I guess of these kind of options that we have, what would we advise? And a second part of this question is, do you foresee PJM increasing capacity premiums considering forecasted scarcity of capacity by 2030? So I don't know if we want to do that in two parts or
Yeah, do you mind if I
one.
start and I'll hand it over?
Yeah.
I would say we're going to see all of the above. We're seeing more and more standalone storage. We're continuing to see hybrid solar and storage. The loss of solar access to the ITC has been a big question mark, but the price has come down so dramatically that we may continue to just see economic development of new solar with storage. I think Umed's study is really insightful, showing there's a huge opportunity for additional renewables at existing renewables interconnections by adding both more renewables and energy storage. So I think we're going to see that play out. And again, this storage opportunity with thermal peakers is just a relatively less known about opportunity, but where the opportunity can be so much lower cost up front and can happen so quickly. The ability to really avoid those 3 longest development cycle lead times entirely is just a massive competitive advantage in speed to market. So I think we're going to see that too. I think we're just going to see growth across the board. And Umed?
No, I think you mentioned all the points.
Do we want to address the PJM part of this, or do you think that kind of the answer that we're going to see all types of projects increasing?
Yeah.
Kind of
So,
answer that.
like PJM looks like really challenging from a capacity perspective. I mean, there is like almost 40 gigawatts or 30 gigawatts of data centers trying to come online. And the new additions, as Will talked about, as I talked about, the gas additions are really slow. So like there could be a real capacity crunch in PJM, and like we have seen the prices going up, and like even right now, the capacity prices in PJM are around $330 a megawatt day, which is actually lower than the cost of new entry, which is the cost of new entry. As there was a recent report from Brattle, the cost of new entry is around $670 a megawatt day. So there is still scope for prices to go up, the capacity market prices to go up. And like in my opinion, the capacity market prices should remain high because I mean there is a clear signal from the market to bring more firm capacity online.
Okay, thank you. Those are all of our questions for today. So thank you so much to everybody who submitted a question. And especially thank you to our presenters. Do Will or Umed, you have any closing thoughts that you want to leave our participants with?
Sure. I'm really looking forward to supporting these projects and would highly recommend any entity that's thinking about one of these projects engage with a firm like Enertis early so we can help ensure contracts are well structured and so we can help you avoid the numerous potential pitfalls through the complex development of a storage system. Thank you.
Yeah. Does that like our study is available on the project website, scarcity2surplus.com. It has a dashboard, like a paper we have published, so you can find details about more details about the study there.
Yes. Okay, great. Thank you again, Umed, for being our guest presenter and presenting the results of your study. And that dashboard will certainly be helpful to many developers, I imagine. For anyone interested in contacting Enertis for maybe continuing the discussion, if you have questions after we end here today, please use our contact link on the screen. And we will get back to you, and hopefully we can start working together and support the development of some of these projects. Thank you all so much for attending, and we will see you at our next webinar. It'll be another interesting topic, I'm sure.
Thank you.
Thank you.